Have you ever really stopped to think about what's going on inside your body when you take a medicine? Today, we're going to get into the science of how drugs really work with our cells. And you'll see why the simplest explanation, the one we all kind of learn, well, it's a great start, but it's definitely not the whole story. All right, so to kick things off, let's use this really classic analogy. For a long, long time, scientists have thought about a drug molecule as a key. And this key is shaped just right to fit into a specific lock on one of our cells. That lock is called a receptor. Simple enough, right? The key fits, it turns, and boom, it triggers some kind of action inside the cell. So this whole lock and key idea, it has a name. It's called receptor occupancy theory. And the core concept is super simple. The more keys you have turning locks, the bigger the effect you're going to get. It's this really clean cause and effect kind of thing. And of course, scientists have a way to visualize this. It's called a dose-response curve. So you can see here, as you increase the dose of the drug, that's the line along the bottom, the response from the body gets stronger and stronger. But look, it doesn't just keep going up forever. Eventually, it levels off. It hits the ceiling, and that's the absolute maximum effect you can get. Now, what's really cool is how pharmacologists use this curve to figure out how powerful or potent a drug is. They use this measurement called ED50. All that means is the exact dose you need to get to half of that maximum effect. And here's the key part. The lower a drug's ED50, the more potent it is. You just need less of it to get a really big impact. This whole idea was really championed by a pharmacologist named A.J. Clark way back in the 1920s. He's the one who said, hey, the response you see is directly proportional to how many of these receptors are filled up. It was just such a simple, elegant theory. And you know what? For a long time, it seemed to explain everything perfectly. But science is kind of like a detective story, right? You follow the clues, and pretty soon researchers started noticing things. Weird things that this simple, neat little model just couldn't explain. The perfect theory? Well, it started to show some serious cracks. So here was the first big puzzle. Get this. Researchers found that some drugs could produce their absolute maximum effect. That ceiling on the curve we just looked at? But they were only binding to a tiny, tiny fraction of the available receptors. I'm talking sometimes as little as 1%. This just completely blew the old idea out of the water. How could the effect be proportional if you only needed 1% of the locks to get 100% of the result? Well, this discovery led to this new idea of spare receptors. It basically meant our cells have way more of these locks than they actually need to get the job done. So the connection between a drug binding and the effect it creates? Yeah, it was clearly not a simple one-to-one thing anymore. The plot was definitely thickening. And then an even bigger problem popped up. This one had huge implications for real patients. Doctors started noticing that with certain drugs, the effect would just fade over time, even if the patient kept taking the exact same dose. It was like the keys were getting rusty and just weren't working in the locks anymore. This phenomenon is called desensitization, and it was a massive problem for that simple lock and key model. I mean, think about it. The drug is still there. The locks, the receptors are still there. So why is the effect just disappearing? Something major was clearly missing from the picture. Okay, so to solve these puzzles, scientists had to come up with a whole new way of thinking. This new model says, forget the simple on-off switch. Imagine the receptors are in this constant, delicate balance, kind of like a seesaw. And this new theory takes its cue from a fundamental rule in chemistry called Le Chatelier's principle. It sounds complicated, but it's not. All it says is that when you have a system that's in balance and you disturb it, you push it one way, it's going to adjust to counteract that push and find a new balance. It's how systems everywhere respond to change. I know, this diagram looks a little complex, but stick with me, the idea is actually pretty simple. Just picture that seesaw again. On one side, you have receptors in an inactive state, and on the other, they're in an active state, and they're constantly balancing. Now, a drug doesn't just come in and flip a switch to on. No, instead, it's like putting a weight on one side of that seesaw. It pushes the whole system, shifting the balance over towards the active side. And believe it or not, scientists can actually measure this. Now, I know that equation looks intimidating, but don't worry about the math. All it's doing is calculating the net shift in that seesaw's balance. It's represented by that Greek letter delta. And this becomes the real way to measure a drug's impact, not just how many locks it opened, but how much it shifted the entire system's balance. So, this new way of thinking wasn't just some abstract idea for a textbook. Nope. It gave us a real, powerful solution to a life-threatening medical problem that had doctors completely stumped for years. Let's take a look at a real-world example. There's a class of drugs called beta agonists. An agonist is just a drug that stimulates a receptor. It's a go signal. A really common one is called isoproterenol, and it's used to basically jumpstart the heart in an emergency. The thing is, it works like a charm at first, but then its effect just fizzles out because of that desensitization we talked about. And that makes it really dangerous to use long-term for things like heart failure. Okay, but here's where the net shift model predicted something that sounds completely backwards. It suggested that if you combined that stimulating drug, the agonist, with a tiny amount of an antagonist, that's a drug that blocks the receptor, you could actually solve the desensitization problem. Wait, what? How on earth could adding a drug that blocks things help a stimulating drug work better? Well, the proof was in the pudding. Or, in this case, in experiments with rat hearts. And the results, which you can see right here in this table, were just incredible. On its own, the stimulating drug gave a big initial kick, but then it quickly faded. But look at that second row. When they combined it with the blocking drug, they got a strong and, this is the crucial part, a sustained response. No more dangerous drop-off. And that net shift model explained exactly why. Think about the seesaw again. The stimulating drug alone pushes it way too hard, way too fast. So the body system freaks out, overcorrects, and just shuts things down. That's desensitization. But adding that little bit of the blocking drug, it's like a perfect counterweight. It stops the seesaw from getting pushed too far, which allows for a stable, controlled, and effective response. So this breakthrough wasn't just about fixing one specific problem. It actually blew the doors open for a completely new way to design smarter and safer medicines for all kinds of things. What this new model really does is give drug designers a whole new toolkit. So instead of just trying to find stronger and stronger keys to jam into the locks, they can now focus on precisely tuning the body's own natural systems. They can actually engineer drug combinations to create a very specific, stable net shift. And that means we can get therapies that are way more effective and have a lot fewer side effects. Really, the big takeaway here is that we can be proactive now. Instead of just waiting for side effects like desensitization to happen and then trying to deal with them, this research shows we can actually model it, predict it, and control it from the very first moment the drug meets the receptor. It's about engineering the exact outcome we're looking for. And this goes so far beyond just fixing one heart medication problem. This deep understanding of how our cells stay in balance, it just opens up so many incredible possibilities. I mean, just think about it. If we can learn to precisely tune this delicate seesaw inside ourselves, what diseases that seem completely untreatable today might become manageable tomorrow? It's a question that could literally redefine the future of medicine,